79 people there. And what we do in the U.S. is we do SIP number 3, IMO SIP number 3, sort of, the quality of information. Do service. Our services include the authentication. Oh, I wrote it down, so I want to make sure I get it concisely. Services include the authentication of information, the management and exchange of marine safety, environmental, AIS, LRIT, DHS, and GPS information, so that the user has authenticated information. And so I get excited about this because I'm looking for what methods are we going to communicate that information, what kind of assurances do we want for that data. That's what we do. We authenticate that data so that the user knows it has some quality in it. It's not just software quality, we're looking at data quality too. And the next presenter here is Helmut Glasener. And Helmut, and I didn't connect this until I read his bio. The reason why I'm standing here is because of what is the interest that Helmut's work with OSL gave me early in my career, because I've been doing ECDIS marine safety information since 1992. And the first Coast Guard ship, Juniper, that had ECDIS was Juniper. I was on the pre-com detail as the operations officer. So I had to go to Vancouver and get trained by OSL, and I don't know that I met you back then. I was a very junior lieutenant at the time, but that interest has just continued, and multiple times in my career I've touched on ECPINs and e-navigation and all the things we do here, so I get to continue to do it at the Navigation Center. So the helmet, he will share with us a precise radar positioning system solution that serves as a backup to the global navigation satellite system. The system originally was developed for a standalone operation in confined waters, but has evolved to become an interface to existing radar. So it's all yours.
Thanks. I hope my voice holds out here. So I may have to rattle things a little bit here and there. But as Bill was saying, my background and the background of the company is mostly oriented toward electronic charting, and electronic charting together with radar, combined with radar. I'll try and make this work. The first 2 or 3 slides basically show just the electronic chart with radar image overlay. In this case, the green is transparent radar and shows that it really matches the shoreline really well there, as you can see on the right-hand side. All the shoreline matches very well with the radar imagery. And that by itself, of course, triggered a whole bunch of ideas on how you could use it for actual imaging or positioning by using imagery and matching the two together. But not only is that one way of doing things, maybe an awkward way to do it, and there are actually a number of organizations that try to do that on a product type basis. But there are other problems when you have ice out there and it no longer is very clear where the edge of the shore is, or when you have tidal fluctuations that shift the shoreline, things don't match very well anymore. But I'll just show some of the features here. One of the major benefits, and I'm talking about what we learned from that, one of the major benefits was the position verification that the user got. And I'll go on to the next one here. You can see, for instance, on the left, the green radar again matches the shoreline perfectly. In fact, even the buoys show little dots that match the shoreline will match the buoy and the radar. And the feedback we got from the users was that this was the most important thing, that they could get position verification instantly, because the 2 sources of information are from totally different sources, basically. And when they match, there's a very strong likelihood that you've got the right position. And we got that feedback all the time. Up here is another example with the radar image in red. We experimented early on with different colors and so on, and transparent and fake radar information. But you can see the radar matches really well on the shoreline, again, on both shorelines. But when you see an image like this, you see the difference between these two. You know instantly there's something wrong, they don't match. And you see that on both shores. You don't know what's wrong. In some cases we found it was datum errors on the charts. In some cases it was just the wrong position for whatever reason. But you immediately know that there's a problem. And not to trust the system the way it is. So anyway, as I was talking about matching imagery, that's one aspect of it. And we use that primarily as I said, as verification of a position rather than a positioning tool. Although we allow the user on their systems to match the two and then record the offset, how many meters and whatever azimuth, and they would know then what the error was. But we wanted to use a system that was specifically taking range and bearing to objects onshore and calculate a position by trigonometric means, calculate what the position is. So we pursued that particular avenue. On the left there, you see a classic trihedral or corner reflector. We experimented with that for some time, and then eventually also looked at different shape of reflector that would give a wider horizontal azimuth coverage and narrower vertically, because we're only interested really in the horizontal. And eventually patented this concept here, these particular reflectors. But that's how we started with the system. You can see that the reflectors are not very big, they're not very difficult to install, and we can set them up very quickly in many different places to suit best the geometry of the area or access to the area. The radar cross-section of reflectors like this is incredibly high. Most documents I read, most papers I read, nobody seems to emphasize this, that the radar reflector is, in this case, you see the reflectors there sitting next to this car. Although they're a 1 meter corner length, they have the same radar cross-section as that vessel out there, close to 600 feet in size. So when you have that kind of radar cross-section, and corner reflectors are always a point source, so they're easy to bring down to a very, very small point. At any rate, we pursued the reflector concept because we knew from our experiments at the time that this would work very well. We could get accurate positions, we could get positions basically anywhere, any place, and if we wanted a really high degree of accuracy, we would place them geometrically in the right positions. We did a lot of our experiments near Vancouver. As you can see on the background here, steep mountains, lots of reflection coming back, and we wanted to do our experiments in areas where there was strong background clutter, so we could see how well we can discriminate against with reflectors to start with. Now, if you look at this, this is a chart of an area called Beat Cove, where we did most of our experiments. And there are 3 reflectors sitting, or targets in some cases, sitting in this area. And you can see them here on the standard radar image, on an island here and up on shore. I marked them, of course, here with red to show where they are, because you can't tell where they are by the same image. But one of the great things that we developed with our system, with the basically called radar fix system, was to discriminate. And that's really the secret of how well the system works. Discriminate against the background color, where we can totally isolate the reflectors or targets from the background color. And that happens in a fraction of a second. It happens constantly. As the radar sweeps, and as far as it does that constantly. The next slide is a video sequence, a slowed down sequence, basically reducing the gain to show you how that works. You can see up here is one reflector. I marked it again, but this is a standard radar image, and now I'm reducing the gain on it. And I don't know whether you can see, now you see more and more radar imagery disappear until eventually all you see is those 3 points. So it totally isolates it. Except what you're seeing here is slowed down so for basically to show it better. But it happens constantly in a fraction of a second normally. And that's really the power of the system, the way it does that. And it's not only with reflectors, but it's also with other targets. Just to give you a better idea, those of you that like to look at radar cross-section levels and so on, the reflector that I showed, the standard corner reflector, trihedral, is the one on the bottom here in red. And the reflectors you saw with a much wider, as you see, a much wider horizontal response, and a total of 6 dB higher in the Borsa. Then we moved on to east coast of Canada, Newfoundland. The ferry service in Newfoundland deals with some of the most difficult terrain and difficult conditions for ships. Lots of ice in the summer, lots of fog, high winds, and many of the people I talked with that have been there and seen and talked, they said this is the place where the snow and rain only is horizontal. There used to be a plaque, a copper plaque or a brass plaque at the marine terminal, at the old marine terminal. I took a picture of it and saved it, where Marine Atlantic said that winds in excess of 100 miles an hour are not uncommon. On 2 occasions while I was there, in the parking lot, 2 large transport trailers were blown over by high winds. And there's what they call a funnel mountain where the wind comes down through there. So it's a terrible place, the worst place I know for weather. So we picked initially a vessel, about a 450-foot vessel. Oops, here, the Atlantic Freighter. And you see here, these are some of the conditions they work under. And this one's got the bridge at stern, and it's a smaller vessel. We took most of the experiments to start with on that ship, and then the larger vessel, 600-foot ships, we equipped after that at a later stage. This the system I should have mentioned earlier. The systems that we developed with a company called OSL that I started in 1977. Called initially, actually the very first one in 1979 in the Arctic was called PNS, for Precise Navigation System. And then followed with PINS. What you're seeing there is PINS, Precise Integrated Navigation System, because we came to the conclusion that we had to bring all the sensors. Our philosophy was all navigation sensors should be input into that system, so you make use of all the available information. And here you see one of the challenges was that the system they wanted was a completely hands-off system. All they wanted was turn the switch on. The system would scale up and down automatically as they get into the docking area. You see on the left there is one scale. As the ship comes in at 18 knots. It's a screeching halt there, makes a 180-degree turn, and then backs into its berth. And they do that with, you'll see some more pictures coming up in very heavy fog where they can't see the stern of the ship and so on. So it's again, it's a terrible place. And we would have alarms and warnings, for instance here, the distance off the stern, off the dock. We show distance off the bow to the island. There's a little island over here, and so on, together with alarms and warnings. So at any rate, these are the 2 And more or less what